What do you say to people who say that organic chemistry is just memorization?
Yeah, it's funny. Organic can be taught in a rote manner, but it can also be taught in a fundamental manner. And when my classmates studying for the MCAT who are taking like the pre-med version of organic chemistry, and they said it's all memorization. You need to know what Mitsunobu is and how to do a Sworn oxidation, and just memorize where to push all the arrows. But the way that my instructor taught it, this is John Snyder, who is at Boston University, just taught it in the language of molecular orbitals and electrostatic interactions, and it just made sense where things went, like Legos. And so I think there is a way to do it that is less rote. Now, the named reactions, what are you going to do about that? But
What level of organic chemistry is needed for courses you teach at UCSD?
So we have two engineering majors within our department, nanoengineering and chemical engineering. And the nanoengineering students do not take any organic chemistry. Some of them take a polymers class that sort of teaches what they need to know, maybe some radical reactions, some not even some polycondensation reactions, but they don't need to know what happens at the carbonyl carbon. They just need to know what the outcome of the A plus B equals AB. The chemical engineers take an entire year. So UCSD is on the quarter, really trimester system, and they take the full year-long sequence of organic. Most chemical engineers, unless they are pre-med or planning on doing a lot of synthesis, don't need, in my opinion, they don't need the whole year. I think that it's not, I don't want to offend organic chemists because I am one. That's my first language, and I wouldn't be able to do what I can do without literacy in organic chemistry. But there are aspects of most of them are like named reactions that are just not not necessary. There's way too much stereochemistry for engineers. The engineers should know what an enantiomer and a diastereomer are, and a tautomer and an anomer and an epimer, but we don't need 5, 6, 7 weeks on it.
How does accreditation affect the need for organic chemistry in various engineering programs? Is there a need for organic chemistry for nanoengineering? What about for your chemical engineering program?
In the nanoengineering program, there certainly is. So the nanoengineering program is kind of like an interdisciplinary sort of R&D focused major. We enroll about 45 students per year, and they take courses that are have their foundations in electrical and computer engineering, physics. Um, Biology was used to be required, but I actually used to teach the 1/4 biochem class for the nanoengineering students, but we made that an elective now. Um, and the students, many of the applications in polymer science, in polymer, vesicle-based drug delivery systems, polymer recycling, microelectronics fabrication, so photoresist chemistry, that kind of thing, all require knowledge of organics. Also, organic light emitting displays, to a lesser extent, solar cells and RFID tags, things that are that require some knowledge there, and they want to know. So they want to know organic. A lot of them take it as an elective, but the first quarter of organic chemistry doesn't necessarily encapsulate all that they would need from all three quarters. And so it's not really enough to take the first course in the first course in the sequence, um, because they're not getting everything that they need. The chemical engineers, it's an issue of accreditation. And I don't know exactly what ABET says about how much organic a chemical engineer has to take, but I suspect it's 1 year to be consistent across all programs. There are some universities, namely Stanford Chemical Engineering, that got rid of its ABET accreditation, but yeah, but schools in the top five have, the sheepskin effect, and they can get away with doing, yeah, yeah. But even chemical engineers, there is stuff, retrosynthetic analysis, stereochemistry, named reactions. I think about Markovnikov and anti-Markovnikov addition, and where is the epoxide ring going to open. I mean, those are things. There's an opportunity cost to learning those things. That if you wanted to teach a full year organic chemistry course to chemical engineers, you should replace a lot of that stuff with the thermodynamics of self-assembly, with intermolecular and surface forces. How does surface tension arise based on quantitative understanding of electrostatic interactions between molecules and between surfaces? And that is all or that all those processes are all mediated by organic structures, but they're non-covalent interactions. They are derived from van der Waals forces and capillary forces and electric double layer forces, and we should and a chemical engineer who is going to be doing often more continuum based research or product development, process engineering, tends to need to know these continuum properties as opposed to molecular details of electrons moving around.
You mentioned on Twitter that you were working on a proposal for a 1-unit organic chemistry course for engineers. Are you taking stuff out, or are you adding new topics?
So there is a subtractive and an additive component of the proposal that I am considering putting forward. And there would be substantial headwinds at the campus level if you said that the chemical engineers no longer took the normal organic chemistry sequence, because the chemistry departments wouldn't like it. There are TA positions that are associated with chemical engineers. There are FTEs that are related to having a certain number of students in a class, and that boat would be difficult to rock. Chemical engineering at the, let's take the, I don't know, top 30 engineering schools are quite well populated. It's at UCSD. We used to have 250 chemical engineers per year. We had a huge number. Maybe it was 200 at max. And there are a lot of campus resources that flow to chemistry departments to serve that student population.
How does the availability of teaching assistantships affect resource allocation in chemistry versus engineering labs?
Chemistry departments complain about having to, serve the pre-med students, the biology students, the engineering students, but then they get all these TA resources and faculty positions, in fact, to service the load. And it affects graduate education in those departments as well, because you can string together a bunch of TA ships and offer first year students the ability to rotate, which you generally can't do in an engineering school without another source of funding. It allows PIs in chemistry departments to overhire, to have bigger research groups. It allows them, as a result, to have the basis to get more lab space, more fume hoods, and in part, this is also kind of an interesting difference between chemistry and chemical engineering, is that the salaries are higher in engineering, but the startups are lower. Startup packages are lower. But in chemistry, the salaries are lower, but the startup packages are sometimes 100% larger. And also, all of these TA ships are available. Sometimes in engineering, a student hasn't had a TA ship, and they, in some programs, they need it for their diploma, and you have to find a way to like shoehorn the TA ship in their the quarter before they graduate or defend or something like that, and that's something that happens. But on the plus side, they're supported the whole time, and they're not overburdened with teaching unless they want to teach after they graduate, which would be a bad thing, right? Because they don't get the experience.
In a hypothetical one-term course in organic chemistry for engineers, would there be a lab component? What about nanoengineering versus chemical engineering?
Okay, given the two cases, chemi and nano-e, I think in nanoengineering, I would not propose it as a lab, because it's not part of our ABET accreditation, and it would probably be an elective. It's just way too hard to change, the core, and especially if a student is interested in more of the electronics and materials, like hard materials aspects, then they wouldn't need this class. In chemical engineering, if I could be king of ABET and loosen the rules as to what topics needed to be covered in a year-long organic course for chemies, the lab would certainly stay.
What would you call an organic chemistry course intended for nanoengineers or material scientists?
Yeah, what I would probably end up calling it like molecular engineering, as opposed to organic chemistry for engineers. It would have a title that was more like how can you apply continuum principles to molecular species, and that's kind of how it would go. Structure, some reactivity, non-covalent interactions.
What courses do you teach now, and how have they influenced your ideas on what knowledge of organic chemistry is needed for engineers?
So the classes that I teach now really do inform this interest. The class that I've taught 10 years in a row is intermolecular and surface forces, which is a graduate course for all of our incoming nanoengineering students, graduate students, but a lot of our senior undergrads take it, and most of our chemi grad students take it as well as an elective. And I'm not sure if you're familiar with the late Jacob Israelishvili, formerly of UC Santa Barbara. He's a chemical engineering was a chemical engineering professor who wrote this brilliant monograph on the topic. The title's just called Intermolecular and Surface Forces, and it builds up the everyday phenomena of self-assembly, adhesion, surface tension, energy dissipation, friction, lubrication from dipole, induced dipole, van der Waals force, hydrogen bonding. And it's such a beautiful, self-consistent theory where you can go in any page in the book and it refers back to some molecular principle you learned in chapter 2, and it's just the best monograph on any any theoretical topic that I've ever seen. And I I tell my students when they start in that course that this is the most important course in the physical sciences that is not taught at every university, and probably only taught at 20% or fewer universities, because it explains, not all of the interactions of matter and the changes that it undergoes are changes in movement of electrons. I mean, how many reactions do you see? Like there are reactions going on in your body, but the the reason that tape sticks has nothing to do with movement of electrons. The reason that that you can walk along the floor without circling the globe is the reason that there are oceans. The reason that that there are organic compounds in the air. None of these things involve reactivity. They all involve electrostatic forces and forces derived from van der Waals forces, of which the dispersion component is ultimately determined by fluctuations of electron clouds and therefore quantum mechanics. And yet we spend all of this time concerned about what the formal charge is of an oxygen atom, in the tetrahedral intermediate, in a carbonyl, in a cyanohydrin formation, which 99% of scientists will never see, and it will never be important in in their day-to-day work. Why does how do composite materials work? What is the van der Waals pressure in an organic crystal? If I take one of these hard Jolly Rancher candies, which is basically a van der Waals solid, and I try to pull it apart at a two-dimensional cleavage plane, the force holding it together, the pressure holding it together, is about 5,000 atmospheres, and you can break it apart without breaking a single covalent bond. That's just how strong the van der Waals forces are at at 0.2 nanometers distance, and so the behavior of matter is dictated by these processes that we barely talk about. The discussion of van der Waals forces at the college level barely goes beyond what's mentioned in 10th or 11th grade high school chemistry. There's dipole, okay, that's obvious, dipole-induced dipole, and then there's something called London dispersion interactions, which are taught to us as being weak, because after all, the cohesive properties of methane and ideal gases are relatively weak. But what is not taught is that paraffin wax and candles are predominantly held together by London dispersion forces, which are very strong if you have a molecule of appreciable size, and completely dominate the dipole-induced dipole, or hydrogen bonding forces. Once you have 3, 4, 5 carbon atoms, that's it. That's like, even acetone has a dipole, but its properties are determined mostly by the fact that it's big and it has a lot of polarizable electrons. My other primary course is Nano 101. It's now called Nano 11 because we teach it to freshmen, and you can't have a 3 three-digit course number for a lower division, and we go through. It's 10 weeks, but we spend about a week each on size confinement effects, optoelectronic processes, spectroscopy, quantum mechanics, micro and nanofabrication, applications in energy, biomedicine. We do spend some time talking about colloids and interfacial properties that are dominated by nanoscale forces. And it started out as quite a traditional course with homeworks and exams, but it's very project based now. It's as experiential as it can get without being in a lab. We do a lot of thought experiments and projects and library research in it. That's facilitated also by the teaching style that I use, which is all of my classes are recorded. They're all on YouTube actually, and the students use those recordings as the video textbook, and then the class period ideally is like the Late Show. It's a variety show with a monologue from me, and then a bunch of problems that the students do, and then some thought experiments and some and our projects in the last third of the course.
Your approach to teaching sounds like flipped classroom active learning. Isn't that standard practice now?
Standard parlance, but not widely practiced. I mean, it's widely practiced, but it's I would say fewer than 25, probably fewer than 20% of faculty are teaching this way. In my
Do you think the preference for flipping the classroom depends on the age of the instructor?
It would be higher for faculty less than or equal to 40, I would say.
Has the percentage of faculty using technology or active learning approaches changed recently, and why?
Yeah, I think COVID has changed it. I think that asynchronous instruction or the production of videos by faculty members that can be watched anytime is a it's halfway there to flipping a class. But the original proponent of peer instruction, Eric Mazur, that were kind of he was one of the pioneers. He doesn't he doesn't the use of videos is not his preferred delivery mechanism. It's still a book, but it's a book that you can interact with in real time, and so a book that you can highlight. Yeah, like an ebook that you can see other students' notes. And
Do you prefer books or videos for your flipped classroom modalities?
if my flipped classroom modality was a book as a pre-reading, I don't think I would do it. I think it has to be, for me, it would have to, the recorded lecture is the hook for me.
Do you think active learning is really more effective than traditional lecturing in terms of student outcomes?
So that's always, I mean, it's difficult to do a randomized control trial in educational methodology, because you kind of know what the outcome is going to be, and you don't want to really disadvantage the control arm of the study. And yes, if you're forcing the students to read before coming to class, they're going to do better. And that's regardless of what you actually present in the class. I would, I suspect that the flipped aspect is like icing on the cake. The fact that students are working together in groups and teaching to each other, unfamiliar concepts. And I should probably walk back something I said. In the peer instruction active modality, you can definitely see when you do clicker based or on Zoom poll based questions where before you use the breakout rooms, the response is maybe 35% correct, and then 5 minutes later, you after the teams have worked together, it's 85% correct, and that's almost like a magical effect. But it's like, does somebody really explain it to the other team members, or just, I mean, I guess they have the best argument because logic of the best solution wins out, or is it like, hey, I actually did the reading, this is the answer? I don't know how much of it is that. um, but there are ways of enforcing the reading using daily quizzes. Actually, this is what I do. They have to submit a quiz online before showing up to class. But yes, your point about flipped classroom versus active learning is well taken. That strictly speaking, you can flip a class just by asking them to do the homework in the class without any active component. But the active part is the engagement.
You were trained as a chemist but now work in an engineering department. How has your status as an outsider affected your view of different engineering disciplines?
Among engineering disciplines, you have disciplines that are more immediately connected to products and services that people use every day. So more development, and then on the other side, you have things that are more research. And the research disciplines are the newer engineering departments: bioengineering, nanoengineering, originally computer science and engineering, but now that's directly applicable to everybody's life. But then the traditional disciplines of mechanical and aerospace and chemical engineering are more on the development side, that somebody could get a job with a bachelor's degree and have a reasonable expectation of the project that they work on is going to end up in a product the next year. Or they're optimizing something that's already kind of exists that they need to make better. A Chemi, an EE, a computer E has a Mech E have very few problems with getting a job out of undergrad. The more research-based engineering disciplines that use engineering science, if that's a thing, I think it is. There's something about application. We generally care about higher order phenomena. It tends to be in the field of chemi, mechy, material science. It's more continuum and less molecular, and also less biological as well. It's because biology is hard to treat as a continuum system, because you have all of these biochemical and cellular pathways and neurological pathways happening all the time. There's so much idiosyncrasy between individuals, especially in medicine. If you're a biomedical engineer and you make a prosthetic knee or a pacemaker or something, the reaction, it needs to be tailored more so. There's more idiosyncrasy. If you are a nanoengineer, there are a couple of fields that lend themselves well to bachelor's level employment, namely microelectronics, because if you're working in the clean room, you know how to process semiconductor wafers. But if you're working in drug development, then you're on the same footing as chemists, even though and biologists and natural scientists. And even though you have the engineering mindset, hopefully created as a result of this 4-year program, the problems that focus on that scale lend itself to are more messy, let's say, in nature. Bachelor's level in this context means, let's say, 1 to 2 years out of undergraduate, like the job you get as a fresh graduate.
How did you become so engaged on social media, YouTube, and podcasts?
So it started with the recording of my course lectures, and it was like asking for forgiveness is better than permission or whatever. And then I had a bunch of them online, and I first started doing it for when I was traveling and I couldn't make the lecture, so I would record one, and I built up a few, and I'm like, you know what, I should record all of them. So 20 calendar year 2017, I recorded the whole intermolecular course, the whole polymers course, the whole nano 11 course, and I got 70 hours of stuff right there. I think the polymer course is the only is the, it's clearly the most popular polymer chemistry course on YouTube.
How do you continue to grow your subscriber base?
Frequent updates encourage subscription, because that first year I was posting sometimes 3 times a week. I also had I was also the director of the graduate student and postdoc scholarly talk series, where I would have speakers come in, but I gave half the talks myself. And I would record the ones that I gave, and they would be on scientific writing. Actually, I wrote an article called "The Garlic, Shallots, and Butter of Scientific Writing" that was in Chemistry of Materials. So it became I think the content is like evergreen because it's science and issues of importance to grad students and postdocs and early career faculty members and the interested public. And when they search for certain topics, sometimes I'm the only hit that comes up, and then they find other stuff on there that they like, and they share it with friends. And my Twitter started after YouTube, but Twitter has definitely helped bump up the numbers. But even if I don't share anything, if I post new content that's just me talking, actually the interviews do less well. But if it's just me talking and it has like a clickable headline, then I'll get 1,000 views in a couple days.
How do you manage social media with other time commitments?
Yeah, I have it blocked on Firefox completely, and on Chrome I have a 10-minute timer for Twitter, Facebook, CNN, and the New York Times, because I can't. It's just an engineering control, because I would just get stuck in loops. YouTube I can watch an infinite amount of, but I don't tend to waste time on YouTube. It's mostly Khan Academy and